All right, so let's start by reviewing some function basics. And you can start by reading the objectives. I'm not going to take the video time here to read through those, but let's get right into the definitions. So a function is a rule that assigns to each element of one set, that's the domain, and it assigns exactly one element of another set, and that second set is what we call the range. A function can also be thought of as a set of ordered pairs, which can actually for us a lot of times come from a table of values in which no first coordinate is repeated. So that's another way to define a function. The domain, something that I will ask you to identify, is the set of all inputs where the independent variable is another phrase for the input variable. So input variable is the same thing as the independent variable. So when you think about your typical XY coordinate plane, that is what you're most used to referring to as the X. The range then is the set of all outputs. So the range is the set of all outputs. And again, the dependent variable now is synonymous with the output variable. So again, if you think about your typical XY coordinate plane that you're most familiar with, that dependent variable is the Y variable. So these are some of the basic vocabulary that we have here. So now let's look at an example. So well, actually, before we get to our example here, a little bit more in the vocabulary, sorry. So a function expresses how a dependent variable changes with respect to an independent variable. So it expresses how a dependent variable changes with respect to an independent variable. So basically that dependent variable is a function of the independent variable, where we will write our ordered pairs as the independent comma the dependent variable. All right, now our domain, once again, set of all input values. For us in this course in particular, we want to focus on the ones that make sense, kind of in practical terms, for that independent variable. So if we're talking about time in general, time we only think of as a positive measure. And then when we get into specific examples, we'll be looking at data and maybe in a particular, like in this example down below, we'll see a range of years or domain of years. So now going on to talk about the range. So the range is the set of all the output values that come from that determined set of independent variable values or the domain. So as we kind of move forward here, similar to a college algebra course, there's really three ways that we typically would express a function. We would talk about it in table form, in some sort of graphical form, and then also as an equation. Now typically in like a college algebra type course, you might start with an equation, look at a table of values, and then go to the graph. We're going to often start with a table of data, get a graph, and then maybe fit an equation of best fit to that set of values. All right, so now an example. So here we have some data that corresponds the lung and related mortality rates from lung cancer and other related cancers. And then that is the dependent variable as a function of the independent variable, which in this case is time in years. So let's look at determining a few facts and questions from this. All right, so we noticed that each year, if we look back, had exactly one output, which was the fatality rate, so it was a function. So each input had exactly one output. You could also look at it as a set of ordered pairs and notice that no first coordinate was repeated. So as we identify then kind of which variables, the independent and the dependent, the fatality rate, that was our dependent variable. So fatality rate was our dependent variable. as it depended on the year, and the year then is the independent variable. So the year kind of passes independently. That's another way to think of it, of the fatality rate. Another way is we're looking at graphs of data. So if I was to graph this in Excel, I have my year as my independent, and then my mortality rate is my dependent. And so there's our graph. So what we want to do is take a look at the domain and the range of this graph. Now, sometimes if I only give you a graph, you might have to estimate some of these starting and ending values for the domain and range. We actually have the actual data set here, so I'm going to write down and flip back over the numbers from the actual data set. So the domain you want to think of as you're looking at your graph from left to right, basically your smallest input value, or typically like an X type of value, and then all the way up to your last independent or X value. So this data started in 1981, and then comma up to that last year was the year 2013. This is what we call interval notation, and so the brackets just kind of say we're including those endpoints in our domain here. All right, the range then, we might have to look back. The range was the data value, the smallest, so we're looking at the output values as we go from least to greatest. So the smallest Y value occurred right here in that last year. So that smallest Y value, pardon my flipping, is 43.4. And then all the way up to the largest Y value, which is sometime in the early 90s there. Let's flip back and look at our early 90s. And it looks like our biggest Y value in there was 59.3. So the largest output, I've said Y, but that's just how we are more used to thinking of the input and output, 59.3. So as we look at our range, it's everything starting at 43.4, kind of the smallest value, up to the largest value. So in an algebra class, we might get a lot more particular about this, but this is kind of loosely how I want you to think of domain and range. So smallest to largest value in the independent variable, and smallest to largest value in the dependent variable. So let's look at an example, and this is one where we're going to have to estimate because I'm just giving you the graph, and we don't, we don't have the actual data set. So the independent variable here, our input variable, is the pH of water. So the pH of water, oops. Our dependent variable then is the number of tadpoles. So that's the output, or the Y variable. So that's our number of tadpoles. So the domain, we want to look at the set of all input values. So it looks like they start, the smallest input value for the domain looks like it starts around 5.5, and then all the way over to the last input value is the 8. So my domain looks like it goes from about 5.5 all the way up to and including 8. The range here starts just over the 20 line, so I'll maybe say 21, and then all the way up to the largest output value here looks like it's just under that 90 line. So I'm going to say from 21 to 89. If I wasn't sure, I could say 20 to 90 just to be safe. So again, that's our range. Now, as we start to move into some of these graphs, we want to think about how we can fit the best curve that might model this data. So something that I want you to recall from your algebra days. So this is what we've already talked about extensively. So data that has kind of a correlation, a linear relationship to it, a constant perhaps rate of change, modeled closely by something with that linear model. This is when we would fit that kind of degree 1 polynomial. Now, a quadratic, this is the same thing as saying a degree 2 polynomial. Or I think in Excel they call that order 2, an order 2 polynomial. So that's going to apply when we have data that kind of has one turn in the scatter plot. So maybe something like this or something like what we see down below. Data that has two turns in it, this is going to be a cubic model. Cubic, if you remember this algebra vocab, is a degree 3 polynomial, or we might call that in Excel, they might call that an order 3 polynomial. So suppose we have this data set right here. It is crop yield depending the dependent variable on the average summer temperature. And suppose that Cassie is a researcher with the Department of Agriculture, and she noticed that different crop yields depend on the region of the farm, and she thinks that that region has to do with the summer temperature, the climate. So this is the data she's collected. So first question, most appropriate type of regression, thinking about the three options above, when the data has one turn in it like this one does, we would fit a quadratic model. Now be careful, again, quadratic, sometimes we hear quad and think 4, but quadratic models are actually those, again, degree 2, or what Excel is going to call an order 2 polynomial. So that's what we would fit in Excel. So suppose that is in fact what Cassie did, and this is the equation that she found was the equation of best fit. So maybe if I were to draw it, maybe this is the degree 2 polynomial that she fit, and that's its equation. We are now asked to predict the crop yield, so that is our dependent, or what is most typically then our y variable. So we want to find y when the average summer temperature, so that is our input, or what we would think of as our x variable, is 13.5 in degrees Celsius. So let's sub that in and see what we would get. So y would equal negative 0.06 times 13.5 squared plus 2.2 times 13.5 minus 14. And so, sorry, I got to get my calculator. I wasn't totally prepared. This is my first video I am recording in a post-coronavirus world here. All right, so let's sub this into our calculator. So I have a negative 0.06 times 13.5 squared plus 2.2 times 13.5 minus 14. And we have 4.765. And our label here, as given by the graph, is, I guess that's just read as tons per hectare. And I apologize if I did not pronounce that correctly. Okay, so that's how we might use a quadratic model. All right, so those are the types of things we're going to be doing in Excel. So if we just kind of take a look at just another quick observation here before we end this first video. So in Excel, let's say we went back to that original data set that we opened with. I can make Excel fit a line to anything. There's a phrase we use sometimes with stats programs, which is garbage in, garbage out. Like, you can fit a line to it. This is why it's so important that we're looking at the data and we're realizing the r squared is terrible at a very low value of 0.3385. Low r squared is going to really reflect how meaningless it is. So if we observe the r squared, and let's maybe add the low value of that r squared, we're going to see how meaningless would be in terms of using it to make any predictions. You know, look at that. It's right twice. Even a broken clock is right twice a day, right? But everywhere else it has absolutely no practical meaning here. So this would not be a good choice to fit a line to this. So hopefully as we look at this, what we're seeing is it kind of has one turn in it. So we're going to do some nonlinear regression, and that would be fitting, in this case, maybe a degree 2 polynomial, that quadratic regression. So in the next video, we'll start looking at how to do these things in Excel.